Okay, so this is going to be a little lesson about light and what light waves are, and then also a little bit about where light comes from as far as atoms are concerned, and also how we distinguish between the electrons in an atom that are going to participate in bonding and the electrons that do not. So light is a kind of radiation called electromagnetic, which means that it affects electric fields and it affects magnetic fields. Not real important, the details on that, but it is important to know that light or electromagnetic radiation covers more than just what we call visible light. It covers everything from radio waves to microwaves to infrared radiation, ultraviolet light, cosmic radiation, X-rays, and of course, visible light. So you can see a picture here of waves moving along. And so there are two waves that are kind of moving together, the vertical and the horizontal ones. And those are the ones that represent the blue, the electric field, and the red, the magnetic field. And so this field, or the strength of the pull of electricity or magnetism, varies throughout this wave. And as I said, that part of it isn't real important. What's more important is remembering that when we say electromagnetic radiation, it refers to light, but it also refers to these other types of radiation. Okay, so what I want you to be able to understand and to identify on a wave are some of its features. So we have the wavelength, and the wavelength is the distance from one part of the wave to the same part of the next wave. So usually we measure it from peak to peak, as you can see on these pictures here. We might also do from the bottom, which we would call trough to trough, but it really can be anywhere. And we use this symbol, it is the Greek letter lambda, and it looks like an upside down Y, and that is a measure of wavelength. And so you can see these two waves have different wavelengths. The longer one is the top one in red, and the shorter one is the bottom one in blue. And this kind of matches visible light. For visible light, the red end of the spectrum tends to have longer waves, and the blue or purple end of the spectrum tends to have shorter waves. Now we might also, so you can see wavelength is here illustrated on going trough to trough, the bottom to the bottom, but we might also measure how tall the waves are. So that's the amplitude. And so you can see that this first arrow here on the left measures the bigger wave with the higher amplitude, and then the other arrow next to it is the lower amplitude. And then we might also measure frequency. Now, frequency has to do with how fast the wave is moving. So it measures both the distance that the wave travels and how many times it does that per second. And so per second would be a unit called hertz. So you'll see hertz from time to time. And different waves will travel at different speeds, but light, whether it is microwaves or X-rays or visible light, it all travels at a constant speed. That speed depends on the medium, but air is pretty close to a vacuum, which is the fastest that light can travel. And that's as fast as anything we know of can travel. All right, so this is kind of illustrating some of the different types of radiation. You can see visible light is right there in the middle, and it's very narrow compared to all of the others. And so what that means is there are very few wavelengths, a very small range of wavelengths or sizes of waves that our eyes can interpret and send a signal to a brain to say, hey, I see something. And so there's a very good reason for this. when we go to the left here, we are getting to smaller wavelengths. So you can see wavelength at the top there. So gamma rays have very, very small wavelengths, and the bottom has frequency, and the frequency increases to the left instead of decreasing. When we have a very high frequency, we also have a lot of energy, and that energy is high enough so that it can do damage. So our eyes don't function so that we can be able to see light that is going to be damaging to us. And so that way we're not trying to look at something that is producing a lot of X-rays and things like that. And then on the right-hand side, we have the frequency is lower and the wavelength is longer. And these are wavelengths and frequencies that are at a low enough level that it's not really moving the electrons too much within the atom. And so it can't really send a signal the same way that visible light can. You can see here that the visible light is kind of spread out at the bottom, so you can see the range of colors. It's sort of a reverse rainbow here, so going from violet on the right to red on the left. We are able to see in this range, most people have 3 different types of cells called cones that interpret the colors red, green, and blue. And so all of the different colors that we can see are based on combinations of how intense the red, green, and blue are. There are a handful of people that can also have a 4th cone that detects another color. And then there are some people who can see a little bit into the ultraviolet. That is not common for most people. Now, in contrast, if you take things like birds, bees, butterflies, they have many, many more cones and can see a much wider range of colors than we can. All right, so remember that when you compare colors, red is the longest wavelength, the lowest energy, and the lowest frequency. And so this is going to be important when we talk about infrared light. Infra means below, and we'll get into that in the next chapter. And then in this chapter, we're talking about ultraviolet. So violet is the highest, ultra means above. So this is higher energy. And that is the kind of light that we are concerned with as far as sunburns and cancer and things like that. All right. So one of the things that we want to talk about is where color comes from. And a lot of times, colored light comes from the emission of light from an atom. And so what you see here are atomic spectra. And so the lines in here are the specific colors of light that are emitted by certain elements. So you can see that at the top, this element only emits a handful. I believe that's hydrogen. And then as we go towards the bottom, we have different numbers of lines, and that's not always in a regular pattern. B, I believe, is sodium. We have a strong yellow line here. So sodium tends to give a yellow color. And then the bottom one is going to give a range of colors. So what happens when we see different colors? If we've got lots of different colors coming at us. If we have something that is black, then all the colors that hit it are absorbed into that black. And that is why sometimes people will say black absorbs heat, because that energy has to turn into something. And so sometimes it turns into the vibrations of the atoms and warms up the black material. Something that is white is going to reflect all of the colors. And so you're going to see all of those come together. So when we get a mixture of all the different wavelengths, to us, it just looks like white light. So when we see color, we have one of a couple of things going on. So one thing that could happen is if we are seeing yellow, like we see on the bottom left here, all of the colors are absorbed except for yellow. And so yellow is bouncing off. And since it is bouncing off, that is what comes to our eye. But we could also have a scenario where we have more than just yellow, but some of the colors are canceling each other out. So if we look at this circle here, this is a wheel, color wheel, that shows colors that are primary and colors that are secondary. So I'm going to use kind of our basic elementary school definitions here. So red, yellow, and blue being our primary colors. We mix red and yellow to get orange. We mix blue and yellow to get green, that kind of thing. So the colors that have to be mixed, orange, green, and purple, would be our secondary colors. So for every primary color, there is a secondary color opposite it, that when the two of those mix, we get white light. So you can see red is opposite of green. And so when we mix red and green, that also will cancel each other out and kind of make white light. Similarly, the purple is opposite yellow and the blue is opposite orange. So if I have this lower right-hand paper here that looks yellow, what could be happening is that it's reflecting all of the colors of light except for what is opposite of yellow. So it's reflecting everything except for this real dark blue here, what we sometimes call indigo. And indigo is being absorbed. So the yellow comes to our eyes and we see that, and the red and the green come to our eyes, but they cancel each other out. And the lighter blue and the orange come to each other and they cancel each other out. And so that's why we see that particular shade. So when light comes from the sun, the most intense light is in that visible range. And the highest one there is right in kind of a greenish range. But this graph is showing the wavelength of all of the shades of light that come from the sun. So we have things that are to the left of the violet, and we have things that are to the right of the red. And those include, the left of the violet is going to be ultraviolet light, and to the right of the red is the infrared. So if we look over to this graph is illustrating to us that even though the most intense light is visible, more than half of the photons, more than half of the energy from the sun that reaches us is infrared. And we get a significant portion, though not a majority by any stretch, of ultraviolet light. So these are the kind of the three most important regions. And we'll talk about infrared a little bit more in the next chapter. But note that that infrared is going to be right next to the red. And so the light that is in the red region is in that area where we have a lot of it and it's pretty intense. And chlorophyll, which is in plants, absorbs strongly in that area. Chlorophyll also tends to absorb in the blue and purple region, but it doesn't really absorb much in that green and yellow region. And so because of that, it's the greens and the yellows that get to our eyes, and leaves appear green or yellow-green to us because of the absorption of the red and the blue and the purple. All right, so you may have seen a prism before. The way a prism works is, you can see coming in on the left-hand side is white light. When that light hits a different medium, so instead of going through the air, it's going through this glass, it is going to change its speed. But it doesn't change its speed the same way for every wavelength. And so what happens then is that the light bends a little bit. It bends a tiny bit for the red, which you can see is at the top, and it bends more for the purple. So it's going to bend when it goes into the prism, and then when it comes out of the prism, it's going to bend again as we go from the glass back into the air. And this is how we can separate light into the different colors. All right. The next couple of slides I'm going to leave in here, and I'm going to try and create a video so that you can see some of this, but this is based on around an activity that I do during the regular year using phosphorescent paper and different colored lights to see how those colors affect the phosphorescent paper. We also will use ultraviolet beads, and I'll try and show you those in a video as well. Okay, so we've seen that light has different wavelengths and different colors have different wavelengths. We've seen that light bends when it changes medium. And you can actually see this when you are having a straw in a glass of water where your eye may look at it and it looks like the straw bends or breaks as the straw enters the water. And really, that's just that same effect of the light bending in the water and making your eye perceive the straw as being in a different location than it actually is. Okay, so let's talk about why atoms are releasing these different colors. Reminder here for our structure of the atom. We know that there is a nucleus and that contains the protons and the neutrons, and they're just going to stay there. We're not real concerned about that. And then we have electrons. Now the electrons, we talk about being in a cloud around the nucleus, and sometimes it's really useful to think of it that way because they sort of take up a lot of space, even though the individual electrons themselves are very small, they're just kind of running around. But it is also really helpful to understand that they are in different energy levels, which we think of those energy levels as being kind of like an orbit of a planet around the sun. And so you can see that this electron here is in the orbit that is closest to the nucleus. All right, so this is an illustration that when we put energy into an atom and it hits an electron, that electron can be pushed to a higher energy level or an outer energy level. So that's when we absorb energy. So when we talked about the black paper absorbing light, this is what's going on, is that light is being absorbed into the atoms and the electrons are being pushed to an outer energy level. And if that light doesn't end up being reflected or transmitted at all, then what ends up happening is that the electron causes the atom to vibrate. Another thing that could happen is that the electron could fall back down into the original energy level. When that happens, we release light. So you can see the arrow leaving. So often when we get light, it is coming from, say, a fire or something that is glowing. That is something that we have put energy in, say a light bulb, we've put electricity into, fire, we've put heat into, and that pushes those electrons up to higher energy levels. And what we see is the energy that's being released as those electrons are falling back down to the bottom energy levels. All right, this is an image, I believe, that is from your textbook, kind of illustrating all of these things at once. So we have on the left-hand side, the absorption, the zigzaggy line is the light coming in, and it pushes the electrons to outer energy levels, one on each side here. And then emission is the other one. The electron falls back down, and we get that zigzaggy line of light that is leaving, okay? Depending on how many energy levels that the electron moves, so you can see on the left hand of each of the atom, the lower left of each atom, it is just moving one energy level, but on the upper right hand, it is moving two energy levels. So two energy levels probably is more energy. And then how far apart those energy levels is also going to determine that. So based on those two factors, you might have different colors of light. So you might get green light if we have a transition in between these two energy levels, red or infrared going between just one energy level because it's lower energy, or ultraviolet radiation if we're doing a whole bunch of energy levels. So more energy levels means more energy. All right, so how does this relate to the structure of the atom? When we think of an atom as being like a solar system, we're looking at what we call the Bohr model of the atom. So I have here energy levels drawn in, but it's not really convenient to draw all of those circles all of the time. So sometimes we use lines. And so as you saw there, the circle is represented by this line. Now we break up the lines into shorter segments, but for right now, I'm just going to show one solid line for each energy level. So that's the first energy level, and it can hold 2 electrons. It's very close to the nucleus, so it's pretty small. The second energy level comes over, so it's a longer line that can hold 8 electrons. The third energy level will hold 8, but after this point, it gets a little bit complicated because of different kinds of orbitals or places for the electrons to be held. So we're just going to think about these first 3 stages. So I'm going to put the lines there because the energy levels keep going, but they do get more complex. So now let's think about where the electrons are and what that means. Valence electrons are the outermost ones, the outermost ring. So let me go back to our picture here. We have electrons in levels 1, 2, and 3. Level 3 here that has 8 electrons, that's going to be our valence ring. Okay. Those electrons can be shared, and sharing electrons would be a covalent bond, or they may be gained or lost. That would form an ion. Atoms are most stable when that valence shell is full. So usually that means 8, but if we just have that first ring, it would be 2. And so atoms are going to have different kinds of reactions and share and gain electrons until they can get to that stable form of 8. The rest of the electrons are core electrons. They're the inside energy levels. They don't do much. They're not involved in chemical reactions, and they stay where they are unless they're very high energy affects the atom. So if I have a fire or if I have X-rays hitting an atom, then I might move some of those core electrons out. Otherwise, normal chemical reactions, they stay where they are. Okay, so now let's go back to this atom here. Let's say I have hydrogen. Hydrogen has 1 electron, and it goes to the inside energy level. Now notice on the periodic table that hydrogen is over on the left-hand side. What we're going to notice here is that all of the elements that are in that column are going to have 1 valence electron, 1 outside electron. Okay, helium has 2 electrons, so we've got 2 in there, and now our level is full. So anytime we fill up a ring on the atom or fill up a line on the right-hand side, we're going to have a full shell, and that is going to be for a noble gas, that far right-hand column on the periodic table. All right, next element is lithium. It has 3 electrons. That third electron has to go into the next ring. So where is lithium on the periodic table? Right under hydrogen. It has 1 valence electron, and it has 2 core electrons. Okay, similarly, right next to lithium is beryllium. Beryllium has 2 valence electrons. Now remember that helium had 2 valence electrons, but beryllium and helium aren't right on top of each other on the periodic table. And this is because beryllium shell isn't full. It still has room for 6 more electrons. So we kind of start a new column with beryllium. And now let's move on. I don't want to do every single atom. Let's say I do sodium. Sodium has 11 electrons. So if I fill up this row, that row has 8. I had 2 in the row below, so that gives me 10 electrons. So the next electron, the 11th one, goes on the 3rd row. And again, we have 1 valence electron. So hydrogen 1 valence, lithium 1 valence, sodium 1 valence. Okay, this is what gives the columns similar properties. So everything in column 1 has 1 valence electron, and that causes it to form a +1 ion. That is what causes it to behave in a metallic fashion. That is what causes it to be soft. All of those properties that we associate with that first group are tied to the fact that it has just 1 valence electron. And similarly, if I look at the next element, element 12, magnesium has 12 electrons, 2 valence, and so magnesium having two valence electrons is going to have very similar properties to other elements like beryllium that also have two valence electrons. Okay, so what I want to do here is look at a comparison of what I want to do here is to look at a comparison of a representation of an atom with an electron moving and of energy levels with the electron moving for the hydrogen atom. So hydrogen has just one electron. Let's say this electron drops from energy level 3 down to energy level 1. Okay, so as it does that, it's going to release ultraviolet light, high energy light, because the gap between level 2 and level 1 is so great. Now, what if it went from energy level 3 just to energy level 2? That is going to be a smaller amount. So it's going to be visible light and it would appear as red. If we moved from energy level 4 to energy level 2, it would be a greater energy than the red, but not as much as the ultraviolet, because most of the gap between 3 and 1 is that big space between 1 and 2. So going from 4 down to 2 gives us a higher energy color. Anything other than red is going to be higher energy than red. And so we're going to see something that's more of a green color. The next energy level will give us a blue, and then the one after that would give us a purple.